Imagine 3D printing metal parts not on powder, but on a layer of shimmering molten tin. It sounds futuristic, but this is real. Scientists have developed a brand new way to print metals using liquid metal as part of the process itself. And it's solving some of the biggest challenges in modern additive manufacturing. To understand why this matters, let's start with how traditional laser powder bed fusion, or LPBF, works. In LPBF, a laser scans across a bed of fine metal powder, melting it layer by layer to build a 3D object. It's an incredible technology that's revolutionized aerospace, medical implants, and precision engineering. But it's not perfect. Each layer of powder acts as both material and support, and that design comes with trade-offs. For one, it makes in-situ control, like adding magnetic or ultrasonic fields, almost impossible. And because the laser repeatedly melts and reheats small regions, it creates steep thermal gradients, meaning some areas cool too quickly, others too slowly. The result? Uneven microstructures, unpredictable grain patterns, and mechanical properties that vary from one part of the object to another. Then there's the economic side. In every build, less than 10% of the powder becomes part of the final object. The rest, over 90%, sits unused in the chamber. It can be recycled, but only so many times before it degrades. That waste drives up cost and complexity. Now imagine a version of this process where the powder layer doesn't sit on more powder, but instead floats on liquid metal. That's the breakthrough idea behind liquid metal-assisted laser powder bed fusion, or LMALPBF. In this approach, a thin layer of powder rests gently on a pool of molten tin, which has a low melting point and exceptionally high thermal conductivity. When the laser melts the powder on top, the liquid tin acts like a smart thermal buffer, pulling heat away rapidly and evenly, preventing hot spots and cracks. And since tin is liquid and recyclable, it drastically cuts down on powder consumption. No more wasted material, no more static powder beds. But the real magic is in what happens inside the metal itself. That smooth, uniform heat distribution allows the molten steel to solidify with incredibly fine grain structures, some as small as a few hundred nanometers. These fine grains act like a natural strengthening mechanism, giving the printed metal both high strength and flexibility. When researchers tested the process using austenitic stainless steel, 316L, the results were astonishing. The printed samples reached a yield strength of over 1.1 gigapascals and a tensile strength of about 1.5 gigapascals, while still maintaining about 7% elongation, meaning the metal was not only strong but still ductile enough to deform without breaking. Even more interestingly, the microstructure revealed a mix of heterogeneous grains, some submicron sized, others slightly larger, creating an ideal balance between strength and toughness. Within the fine regions, niobium and chromium-rich nanoparticles formed naturally, pinning dislocations and adding another layer of hardening. It's like the material is self-optimizing as it cools. And because the tin layer acts as a built-in thermal moderator, the process essentially performs in-situ heat treatment, a step that normally requires separate, high-temperature ovens. That means parts come out of the printer with ready-to-use mechanical properties, no extra processing needed. This innovation doesn't just improve strength, it also improves consistency. Every layer experiences nearly identical cooling conditions, resulting in predictable microstructures and uniform performance. That's a huge leap forward for industries like aerospace, where reliability is everything. The implications are enormous. Imagine printing aircraft turbine components with precisely engineered grain orientations, or biomedical implants with graded microstructures, tougher on the outside, flexible on the inside, or even high-pressure energy components that last longer because their internal stress points are minimized. And perhaps just as importantly, it's sustainable. By reducing the need for powder reuse and waste, liquid metal-assisted printing is cleaner, cheaper, and more resource efficient. So what started as a clever materials experiment could soon redefine how we manufacture high-performance metals. By combining physics, metallurgy, and creativity, researchers have taken a process that's been around for years and turned it on its head. From a sea of molten tin, the next generation of super strong, precision engineered metals is being born. And this could be the spark that launches the next era of additive manufacturing.